Okay, so I'm going to talk about limitations of large language models. Okay, so before I begin, I want to give a very quick overview of the kind of research that we do in my lab. We work in three major areas in machine learning. This includes deep learning, reinforcement learning, and natural language processing. Okay, and my long-term research vision is actually to develop interactive learning algorithms that can continually learn from experiences. Okay, so what do I mean by interactive learning algorithms that continually learn from experiences, right? So when I talk about interactive learning algorithms, I'm really thinking about systems that can interact with humans. So this includes reinforcement learning, but it also includes natural language processing systems like dialogue systems, for example, right? And we also work on some of the core machinery behind these two systems, which is the idea of sequence modeling. And when I say systems that continually learn from experiences, so this includes both reinforcement learning and lifelong learning. So most of our work is in the intersection of these areas. And for the purpose of today's talk, I think I'll mostly talk what happened. So I'll mostly, there's no point. I'll mostly talk about natural language processing and a little bit of lifelong learning work on the top of NLP. Okay, so let's get started. As you can see here, this is the new Moore's law, but this time for the size of the NLP models, right? So the size of large language models has been growing exponentially. In 2017, so we had simple things like BERT, which were few 100 million parameters, but now we have models like Search Transformer, which is 1.6 trillion parameters, right? But this is only 2021, so this only gets bigger and bigger every year. And here is a very quick overview of different large language models that are out there. And I think this is a figure from March 2023, and the growth is exponential in this field in the sense every week there are 5 to 10 new LLMs released by different companies and startups, right? So there is a lot of effort which actually goes into training these models. It requires a lot of engineering expertise, it requires a lot of compute money, to train even one big foundation model, right? Okay. And here is a graph which shows the amount of compute that is needed to grow, to train some of these models. Okay, as you can see, as the models get bigger and bigger, the amount of compute that is required also grows exponentially. Okay, so training a state-of-the-art language model might require $20 million or $30 million, right? So in some sense, there's a gold rush for companies and startups to go get their own language model, and so that they can actually start using it in different applications, right? So now we are starting to see this trend that LLMs are used in downstream applications. Now this includes even things like computer vision, reinforcement learning, robotics, more and more fundamental sciences, right? So we use LLMs for physics, chemistry, biology, etc. Right? So we are in some sense treating these language models as task solvers. So you take a language model, then you fine tune it on a task, and you expect it to work well out of the box, right? So now, the core question that I would like to ask in this talk is can we use them as task solvers? So what are the limitations that we need to address before we can use them as reliable task solvers for any task that we care about, right? So I want to start, I'm going to have a series of questions in the outline. I do not want to give everything in the first slide. So this is the first question that we will think about. So can large language models consolidate knowledge? Okay. So if you think about it, human scientists encompasses a lot of knowledge that he or she has learned over the last decades of research, right? So every scientist reads a lot, learns a lot, tries things, and somehow they form this mental knowledge of the picture, the mental knowledge of the field that they are working on, and this knowledge is what leads to new discoveries, right? So now if you want to use language models as artificial scientists, like which is the kind of thing that people are looking at using LLMs for drug discovery, using LLMs for material discovery, etc. Right? Like so, then the core capability that we would expect LLMs to have is somehow they should be able to consolidate the knowledge that they see across time, right? So this work that I'm going to present today, like, is actually like work done my PhD students Gabriel and Jerry. Like, so this is under review at EMLLP, which is one of the reasons why I said put the recordings next week. So EMLLP has an anonymity policy that I'm not supposed to talk about this work until the decisions are out, which is this Friday. Okay, so we are hoping that the work will get accepted this Friday, so then we can release this recording. Okay. So what do we do in this work? Like, so this is the general idea. Let's say I have an LLM, which is trained with a bunch of like news articles, okay, so over time, okay? Now, typically, when a human reads these news articles every day, like let's say there is a political situation that is forming between two countries and you read the news every day, like so you connect things from what you have learned from yesterday and put things in some perspective, right? Like so we have the ability to connect different facts which are relevant or even irrelevant, right? Like so we are really good in connecting the dots, right? Now the question is, how would the representation space of LLMs look like? So if I train a language model with a bunch of news articles, so is it going to represent things like this, like in the left side, like, which means that it is just putting them as a bag of facts, right? Like, so there's no connection between these facts, or it is actually going to make connections between these facts and has the capability to answer a question which requires connecting things, right? Now, if you think about it, like, well, so maybe I'll explain one of these things. So to answer this question, like, so we kind of categorize models as two types of systems. Like, so it's like the system one, system two analogy, right? Like, so we have type one systems, which let's say reads a bunch of these articles, like which says Tom ate an apple, Tom ate a pear, Bob ate an orange, right? Like, so like these are the naive language models that we normally see, which assign some probability for the words. And if you ask this particular language model, what did Tom eat? It's going to tell Tom ate an apple with some probability, a pear with some probability, an orange with low probability because it has never seen Tom eating an orange, right? However, if you think about it, a good system which integrates all these information that it has obtained should have a more definitive answer, like which is Tom ate an apple and a pear, right? So now the question that we ask in this particular project is like, are LLMs more of type 1 systems or type 2 systems? I think the answer is a bit obvious. Like, so most of the current generation LLMs are type 1 systems, okay? But we are just going to prove it more rigorously, okay? Now, how do we do that? So this is how the setup looks like. Like, so you could take a bunch of books, okay? Now, instead of showing all the books together, like in individual units, like, so you can train an LLM, like you can pre-train an LLM by showing parts of the books, okay? I take Lord of the Rings, split it into multiple parts. I take another book, split it into multiple parts. Like, so now I just train an LLM with all these parts, different parts, right? Like, so once I finish this pre-training, okay, so this is how the pre-training would look like. Like, so at every time step, I put some parts, but they are separated in the sense there is no connectors, right? Like, so now I'll ask some question. For example, I'm asking a question from Harry Potter. Now, answering this question would require the model to put together different parts of this Harry Potter story, okay? So if the model really consolidates the knowledge, it should be able to answer this question, right? Like, so if it doesn't consolidate knowledge, like if it's just putting them as a bag of facts, then it's going to fail in this task, right? So this is the setup. Now, we are going to compare two versions of algorithms, okay? Like, so one is where I train the LLM without segmenting the stories. Like, I feed the entire story as input. And there's a second part which is trained with just the segmented things. Okay. And I will ask the same question to both unsegmented training model and segmented training model. Okay. Now, of course, if I have to do this with the current generation LLMs, I cannot feed an entire book into the LLM, right? Like so we're going to use a bunch of short stories that we developed ourselves, like very carefully. And these stories, like, are like typically 5 to 10 lines long, and we have few thousand such stories, and like we're going to train one version of the LLM with unsegmented stories and another version which is trained with segmented stories. Okay. Now, and then I will ask a question like before, like so I'll ask a question to both, and typically this question would require the model to combine information. You cannot answer these questions by just one of the facts in the story. Okay. Now, before I show you like more quantitative results, like here is an actual qualitative result. Okay, so from the two versions of LLMs, like so you see here that the unsegmented model gets it right in this particular example. Okay, so the example actually comes from the previous thing. Okay, it actually tries to reason like from the story and makes the right makes the right calculation here. But the segmented trained, the model that is trained with segmented stories, right? Like, so it gives us an answer, but there are a lot of made up facts there. Okay, so it, in some sense, well, like this is what people call as hallucinations, right? Like, so it hallucinates certain facts which doesn't exist in the story, and the final answer that you get here is not correct. Okay, now this result holds in general, okay, irrespective of size of the model or type of the model. Okay, so this is one of the figures, like where I show in x-axis the number of parameters of the model, okay, and in y-axis you see the accuracy of this test. Okay, so there are here we tested both T5, which is just the base model, and Flan T5, which is the instruction tuned version of T5, just to see if this is just an artifact that could be resolved by instruction tuning, right? Like as you can see here, instruction tuning really doesn't help that much, right? Like so in both the cases, the solid blue that you see here, or the dark blue, is the unsegmented model, and the light blue is the segmented model, okay? So the gap between these two models is definitely huge, right? Like so as you can see here, when you give things in parts, LLMs cannot put them together to answer the question. Okay, and this also like gives us a valid explanation why hallucinations happen. Okay, so here you see the hallucination rate of segmented versus unsegmented training setups. Okay, so as you can see here, well, first of all, you cannot completely avoid hallucinations because they're probabilistic models, right? Like, so they're going to make mistakes. But you see here that the hallucinations made by the unsegmented model is much, much lower when compared to hallucinations made by segmented model, okay? So this also gives us some guidelines on how to use these LLMs, because if you use these LLMs for simple questions where the answer is there somewhere in the internet, right? So they might be able to give you the correct answer without any hallucinations. But the moment you start asking complex questions to LLMs, like so, these experiments basically demonstrate that they are going to hallucinate a lot. So probably that's not the kind of application that you should be using these LLMs for, right? Now, I showed you, yeah?
Yeah, just a little dumb question about when the segmented and the unsegmented models, they output the answers, right? How do you actually extract the answer? Like, what's your criterion for deciding that?
Okay, well, that's a good question.
Is it like a human that checks the text?
Or? Okay, that's a good question. So I was hiding a lot of details here, which I did not tell you how the training setup looks, right? Like so the goal here was really to showcase the results. So we have we have a separate training set for answering the questions. We train the model in the task with the task. Then there's a separate evaluation, and the evaluation is automated. So like
it's like a model that's been trained to pick the text and extract the answer, or like predicting whether the answer is correct.
No, well, I think it is a script which checks whether things are correct. Okay. So it's not a model.
Some kind of like a regex thing, yeah. Like you're looking like
yeah. Yeah. Okay. So I showed you that these models cannot consolidate knowledge, right? Like, so then the next question is like, why is this happening, right? Like, so why do they struggle with knowledge consolidation? Like, so, like our hypothesis is, well, it's also an obvious reason in the sense like it has to do with the training objective, right? Like, so when you train an LLM, like you're really training to predict the next word, right? So this is causal language modeling, but you can also do mass language modeling, right? Like, so but the idea is you try to fill a word, right? Like, and this encourages the model to understand the context in the given sentence or in the given document, right? But there is nothing in the training objective which really encourages the model to look at two separate things and put them together, right? Like, so if I train a model with documents, one saying celebrity is getting married in Miami next spring, and there is another document or news which says hurricane hits Florida. Like, as a human, you read these two, you immediately like guess maybe the wedding is affected by this hurricane, right? Like, so for an LLM, unless it has a good retrieval system which goes retrieve relevant things and put them in the context and then do in context learning, right? Like, so that's a different way to solve the same problem. If you're not good in doing that, so then there's no way for you to connect these two things. Okay, so to summarize, this is the current language model. Okay, so like, so it really models a distribution of facts. Now, I want to highlight that the distribution of facts is not knowledge. So it's just a distribution of facts, right? Like, but what we should really aim for is to develop the next generation of LLMs, like, which would hopefully connect the dots and form knowledge about the world. Okay, so those kind of systems are going to be more useful than the simple LLMs that we have. Okay. Now, one might ask, maybe I don't need to do anything, just scale things up, right? So we tested with whatever the size that we can test in academia. But maybe like if you could go for a much bigger size, one could argue that this gap will close, right? Like, but I would argue that it won't close, well, because like there's nothing in the objective which really encourages the model to do this, right? Like, so most probably the line is going to look like the more solid dash line. Okay. Okay. So now the first question was more about what can they consolidate knowledge, and the answer is no, right? Like, so they cannot consolidate knowledge. I also established that they model distribution of facts, right? It's not knowledge per se. Then the next obvious question is like, if they model distribution of facts, can they at least use all the facts that they have learned while they perform a task, right? Like, so, like, let's say they learn a bunch of facts. Now, can they use all these facts reliably when they perform a task? Okay. So again, the answer is no. Okay, like in one word, like, but we are going to show how that's the case. Yeah.
I don't understand. How is that different from the first question?
So the second question is like, okay, the first question is, can they connect different things to answer, right? Like, so now even if you're in a simple setting where it's just a distribution of facts, like I ask a question, which is based on one fact. Okay, so can they use the fact and answer this question, right? Like, so that's the second one. The second one is like a bit more like, basically like in the second one, like we know their capabilities, like now can they at least do what they are currently good at, right? So this is the work done by Amir Hussain, like a master's student at FILA. So this is also under review at EMLLP, but we managed to put this in archive before the anonymity deadline. So you can go read the paper. Now, as I said at the beginning, like, so we are pre-training this model with the entirety of internet right now, right? Like, so the pre-training data like exceeds trillions of tokens nowadays. People easily train for 1 trillion tokens, right? Like, so, which is almost the entire work, right? Like, so now the way in which we pre-train these systems, like, so as I said before, like is helping us to learn a bunch of facts. Like, so for example, like if you train an LLM like on the entire web and ask a question like this, what is the capital of France, right? Like you would typically do that by the capital of France is slash, right? Like slash is the mask, and LLM could fill that it is Paris. Okay, so this means that this LLM has modeled this one particular fact, which is the capital of France is Paris, right? Similarly, you can ask another question. Obama's birthplace is dash. Okay, so the LLM, when it fills Honolulu, Hawaii, like it means that it knows this fact, right? Like, but these are simple facts, like they are not complex facts which require putting things together. These facts already exist in the internet, right? Now, there are many such simple facts which are modeled by these LLMs, like the birthplace, capital, common sense, linguistic knowledge, etc. Right? So we are going to call all these facts as the acquired parametric knowledge of these LLMs. Okay? So these are parametric knowledge because typically LLMs see the text, encode this in the weights, and when you ask this question, like it is able to answer this, right? So this is the acquired parametric knowledge of an LLM. Okay, so I'm going to show you how to extract this knowledge. Okay, now let's say there is a procedure to extract this acquired knowledge. Okay, now can we verify if an LLM which has, for example, 100,000 acquired knowledge facts can use all these 100,000 knowledge facts when it performs a task? Okay, if not, like what are the reasons why it could fail in applying the knowledge it already has, right? So that's the premise for this project. So there is a common assumption in the literature that like if the model possesses a certain type of knowledge, it utilizes it when performing the downstream task, right? And this is one of the reasons why people train them with lots and lots of data with the hope that they're going to acquire a lot of knowledge and eventually use them in the downstream task, right? Now, a typical downstream task would look something like this. You will take a pre-trained language model and you do some fine-tuning on the task that you care about, and then you use the fine-tuned pre-trained language model, right? And this fine-tuning is often done with like either supervised learning or like instruction fine-tuning, or you could do chain of thought fine-tuning. There are a lot of fine-tuning procedures that are out, like which you could use to adapt your pre-trained model for a specific task. Okay. Now, the question that we are going to answer now is like how much of this parametric knowledge will get applied when you do a downstream task. Okay. So this is the overview of our experimental setup. So we're going to first extract the model's parametric knowledge. Then I'm going to create a downstream task that is tailored to this model's knowledge. Okay. So the task is set up in such a way that the only way in which the model can answer this task, like solve this task, is by using the knowledge, the parametric knowledge, okay? Then we're going to measure the knowledge utilization, okay? And I will also show you like how this is going to vary depending on the downstream task and what is the effect of scaling, etc. Okay, so let's get into the setup. So here is a bunch of facts that you could collect from anywhere. For example, Freebase is a open source knowledge base, which has a bunch of facts like this, okay? Now I'm going to take a pre-trained model, any pre-trained model, and I'm going to extract the facts that are already learned by this model, okay? Now there are many techniques like that exist in the literature. You could do hard prompting, you could do soft prompting, okay? So basically we will prompt the model with each of these facts and collect only prompts where we were successful, okay? So this means that this is like in some sense a lower bound of model's parametric knowledge, right? Like so maybe there are other knowledge which we missed during the prompting, but this is at least a lower bound on like the amount of knowledge that this LLM has, right? I'm going to take this parametric knowledge, okay, and I'm going to use this parametric knowledge, like the data set d theta, to set up my downstream task, and the downstream task looks like this. I'll take a fact like Barack Obama graduated from Harvard, and the task is a question answering task, like where I ask, where did Barack Obama graduate from? And there are a bunch of options. Some of these options are relevant, some of these options are irrelevant, some of them are wrong. There's only one correct answer. Okay. Now I can set up like a bunch of such question answering tasks, right? And I'm going to split that into training and test bed so that I train the model first with the training set. So this, in some sense, teaches the model to use its knowledge to complete the task, right? Like, so if it is successful, then it should have a very good test performance too, right? So that is the setup. Now, the first question is how much of this diagnostic data set can be predicted correctly? Or in some sense, like what is the memory capability of this LLM, right? Like, so like what fraction of knowledge, but here by knowledge, I mean fact. What fraction of facts they can encode? And the answer really depends on the size of the model, type of the training that they went through, right? Like, so here you see interestingly, BERT captures more knowledge than something like OPT. Okay, so now people know that OPT is not such a great model. Like, so probably you should use something like Llama, right? But this gives you an idea of like what fraction of data sets is actually captured by these LLMs. Okay. Now the next question is, let's say BERT can capture 47% fact. Out of this 47% fact, what fraction can it actually use, right? So that gap is the knowledge utilization in the downstream task, okay? And you see that different models have different capabilities, okay? So interestingly, even though BERT captured 47% when compared to OPT, like which is 34%, right? So BERT was only able to use 78% of this knowledge, okay? On the other hand, OPT has better knowledge utilization, like not significantly better, but relatively better, right? So this in some sense tells us like how different models can use their knowledge and like what is their like usage capabilities, right? Like, so which could guide us in changing our objective function or changing the architecture so that we don't have this thing, right? Like, so now this is a summary of both these results, right? Like, so in the red, what you see is the usable knowledge. Okay, that is a fraction of knowledge that the model can use. And in the gray, you see identifiable knowledge, but the model cannot use this knowledge. Okay, so the gap one is really representing the missing facts in the parametric knowledge. But what is really interesting is gap two. Like, so there is a gap two, which defines how much of this knowledge the model cannot use, right? Now, again, like the same question, like, so would this gap reduce if we scale these models, right? Like, so the answer happens to be no. Like, so here you see in the left side, like for OPT, we tried different like sizes of OPT, okay? The red is the usable knowledge and the gray is identifiable knowledge, right? Like, so this gap, we expect this gap to shrink as you increase the size of the model. It really doesn't happen, okay? With Llama, I think we tried 7 million or 30 million things that we could fine tune. Like, I think now we can fine tune like bigger Llama models too. Like, so we're slowly working on the infrastructure, but like, so this is what we had when we published this result. And you see that the gap doesn't change, right? Like, so the ideal gap should be something like this, but there's a bigger gap in all these scaling. So like, now the other interesting experiment is like whatever I showed you is the ideal scenario where like you took the knowledge from the model, like, and you trained it in a nice IID setting, like where you have a representative training test and test it, right? But that is not how we use these models when we do downstream tasks. Like we always use these models in like different novel applications, like where the task might be very different from the pre-training data or objective, right? So then the situation becomes even worse. Okay, so like, so this was the downstream task performance in the IID setting, the one that we just saw, right? So now when you set up an OOD task, like where you train the model with a bunch of relations, but then test it with completely new relations. But these relations do exist in the parametric knowledge, okay? So then you see that the downstream performance is even worse, which means even though they have some knowledge, some facts, factual knowledge, not the knowledge that we saw in the first project, they have some factual knowledge. And so they're going to struggle to use these factual knowledge the moment the task deviates from the distribution of the training data or the pre-training objective. Okay, so these are something to keep in mind when you use these in downstream tasks. Okay, so Any questions? Okay. Now, let's move to the next question, which is, well, so far I established that there are some facts, and even though they are imperfect, you can use these facts when you do downstream tasks, right? Like, it's not too bad. That's why we see a lot of practical applications of LLMs, right? Now, can we use these LLMs as continual task solvers? Like, so what do I mean by continual task solvers, right? Like, so like a general purpose algorithm that I can use to solve many tasks, right? And so imagine deploying an LLM in the cloud, and like customers come with new tasks, and it is like trying to solve these tasks, right? Like, so like there are many benefits in having continual learning systems, right? Like, so like if you don't do continual learning, then you're going to keep separate copies of these LLMs for different tasks, and that's okay with small models, like with a trillion parameter model. Like, you don't want to keep even 5 copies of a trillion parameter model, right? Like, so like ideally you want one model for many tasks, right? Like, so can we do that with the current generation LLMs? So this is like whatever I'm going to present, like in this part, like this is published in JMLR after 2 years of back and forth with the journal. But I'm also going to present only the NLP side of this paper, but this paper has like an equal computer vision side to it. Okay, so I encourage you to go read the paper, like if you care about LLMs, not LLMs, but pre-trained models for computer vision and their capabilities when it comes to functional learning. Okay, so one of the big push from the LLM community is like, so these are general purpose pre-trained models that you can use to solve any task, right? Like, so in some sense, like you have a very good transfer learning that is happening. Okay, so for example, like, so here I show you like a distill bird, okay, which is trained on a split Yahoo QA data set. So there are 5 different tasks, okay, and the only difference between the blue and red is the initialization. Okay, so I initialize the blue with a pre-trained distill bird and the red line with a random distill bird. Okay, as you can see here, there is definitely clear benefits in pre-training, like using pre-trained models in lifelong learning, right? Like, so a pre-trained model, it undergoes some degradation as it learns more tasks, but it is a very graceful degradation when compared to a random model, which gets to like close to random performance, like after seeing 5 tasks, right? So does this mean that I can always take a pre-trained model and do many tasks, like without worrying about catastrophic forgetting, which is one of the main concerns in continuing learning community, right? So that's what we're going to address here. So first, we are going to start with this 5 data set NLP task. Okay, so where there are 5 different data sets in NLP, and like you can read the paper to know what these tasks are. That's not very relevant for the discussion here. And we're going to compare different pre-trained models and their accuracy at forgetting. Okay, so ideally we aim for models with higher accuracy and lower forgetting. Okay, so here you see that larger models clearly undergo less forgetting. Okay, so BERT is better than distill BERT. Roberta, so BERT large is better than BERT base, etc. Right? So larger models undergo less forgetting, like which is at this point kind of established in the sense like very big over-parameterized models have a lot of capacity that they should be able to fit a lot of tasks, right? Now, the other interesting aspect is the diversity of pre-training corpora is also relevant. Okay, so here you see that Roberta large, so Roberta base, which is a small model, and BERT large, they have very similar performance. Okay, even though Roberta base is smaller than BERT large, it is able to match the performance just because it has very diverse training data sets when compared to BERT. Okay, so the quality of data is also important. The size of the model is also important. Okay. However, this all holds when you have tasks which are either in distribution to the pre-training task or task which doesn't have a very different like distribution than like whatever the pre-training data that they have used. Okay, So, so to study, to basically push the limits of these LLMs on like seeing when they would start degrading, right? Like, so we constructed this new 15 diverse NLP benchmark. Okay, so this benchmark is interesting because it has variety of NLP tasks, classification, generation, etc., reasoning, etc., and like it has smaller data sets, bigger data sets. It has data sets which has class imbalance problems, etc. Okay, so this is like a representative of the kind of problems that you would face every day. Okay, and we are going to train all these LLMs in this 15 task benchmark in a continual learning fashion and see how they can hold. Okay, so you see some results here. There are more results in the paper, and as you can see here, the accuracy drops and the forgetting increases with more tasks and more diverse tasks. Okay, so even though pre-trained models are useful, they still undergo significant forgetting when you have totally diverse tasks. Okay, so in some sense, the original continual learning problem is not solved by scale or pre-training. Like, so it's a bit better now, but like I would say we still need to solve forgetting and we still need to think about the core continual learning problem. Okay, so if you really want to put these systems in deployment with many tasks. So the paper also has some analysis on why actually these pre-trained models could have less forgetting. Okay, so here you see the loss contour for like different data sets, like 5 data sets, NLP 5 data sets. See, these two are computer vision, these two are NLP. Okay, so here you see the loss contour without pre-training and with pre-training. Okay, as you can see, the solution lies far away when you have a model which is without pre-training, and they are somehow closer, like and in a much flatter surface when you have like a pre-trained model. Okay, so pre-training, this is also, I think, well, maybe right now this is an established result, but like this work was really done in 2020 or 2021. Okay, so then I think it was still a more active area of research where people were trying to understand like how like the pre-training is going to help with the multitask learning, etc. So in that sense, like it was still a new result then, like so where we showed that you can use a pre-trained model. This pre-trained model is going to put you in a good region of the loss surface, and it's going to be easier for you to do many tasks without forgetting because they are all close to each other. Okay, so on the other hand, like with a surface like this, when you move between tasks, like you're going to have forgetting for the tasks that you did not like that you learned before. Okay, so now I want to switch the focus and talk about other important questions when it comes to deploy these LLMs. Okay, so let's say I want to deploy these LLMs in tasks which are sensitive, okay? Like basically any decision-making task, right? So it is really important that we can interpret the decisions made by these LLMs, right? Like, so now how do I interpret these decisions, right? And so there are a lot of work that exists in the literature. Okay, so but I'm going to present like a very recent work from my PhD student Andreas, like so, which has this really ambitious goal of developing LLMs which can give explanations, but then the important thing is these explanations are faithful explanations. Okay, I'm going to show you a bunch of work in the literature which tries to give explanations for the outputs of the LLM, but nothing has a guarantee that these explanations are faithful. And in fact, it is very difficult to prove the faithfulness of these explanations because we don't have the ground truth, right? If the model might say, this is the reason why I said this, but what's the guarantee that it is a true explanation, right? Yeah.
So these LLMs are trained on, I have a question regarding knowledge, like is the knowledge faithful, or the knowledge on which these LLMs are trained, is that faithful? Because if that is not faithful, and does LLM have an intrinsic way of verifying the knowledge, whether it is consistent or not?
That's a good question. Answer is obviously no, but I think we can prove that like rigorously if we want, right? So I don't think like the thing is when we read, we know what is the misinformation, right? Like I don't think these models have that capability. So that's a very good question to investigate. Okay, so as I said before, there are many approaches in the literature to come up with interpretability methods for LLMs. Okay, so for example, let's say I have an LLM which takes the movie is great, I really liked it, and gives me the sentiment score. Okay, so it's positive sentiment, right? Now, one major class of interpretability methods is called importance measures. Okay, so which basically gives some importance to different words in the text that contributed to this decision. Okay, so in this case, you see that the movie, great, they have more importance. Like also has some importance, like when it detects that this is a positive sentiment, right? Now, there are many ways to come up with these importance measures. Like, so for example, there is this leave one out method, which basically tries to mask every token and see if the sentiment changes. Okay, so here when I mask the first thing, the positive sentiment is still 90%. Okay, so which means there is not that important factor for making this decision. On the other hand, when I move the movie, there's a reduction in the performance, like which is the reason why we put some weight here for the movie. Okay, so and I think if you do it for great, it's going to change the sentiment probably, and that means that great is one of the most important words here, which resulted in the decision, right? Now, there are many such methods that exist in the literature. Like if you are interested in interpretability for NLP, like so we have a recent survey, like so which covers various post hoc interpretability methods for NLP. Okay, so and LLMs. So by post hoc interpretability, we mean like you have a trained model. Now you try to understand like the model's decisions like after training. Okay, so that's what we call as post hoc. Okay. Now, there is also opposite of like on the other extreme of interpretability, which is intrinsic interpretability. Okay, so post hoc method includes things like leave one out or occlusion based methods, or there are gradient based methods which tries to compute like how much the gradient changes if I remove a word, etc. Okay, and there are also intrinsic methods, like for example, like attention. Right? With attention, there are I think a series of papers saying attention is an explanation, attention is not an explanation. Then there's another paper that says attention is not an explanation. Okay, so there is an ongoing debate on whether attention is interpretable or not, but there are like also other methods, like we're going to call these intrinsic methods. Okay, and there are benefits for both, right? Like so, for example, with post hoc, like the black box models can be explained with post hoc methods. You don't need to look inside the model, like to add that attention map or etc. Right? So it's going to be more general. Like you can use black box model with any model that you have. On the other hand, intrinsic methods are only for methods that these models that are intrinsically interpretable. Okay, and now I think there is a lot of work in the literature which tries to argue that one should do post hoc or one should do intrinsic, like right. But one of the major issue with both these classes of approaches is, let's say I have a post hoc method, like the masking method, right? Like I mask things, and when I mask the thing, the prediction changes. Now, what is the guarantee that this change in prediction is like the right explanation for the model's behavior, right? Like, so it might also be the fact that when you mask things become out of distribution. So the prediction changes, right? Like, so we might be falsely interpreting this out of distribution issue as like an explanation of the model, right? So this is one of the major issues with a lot of these post hoc methods, okay? Now the issue with intrinsic methods is like the whole point that there is a whole debate on whether attention is interpretable or not, right? That's the core essence. Like, so any intrinsically explainable method, we construct it to explain things, but again, there is no reason the model should follow these explanations when making decision, right? Like in some sense, there is no grounding for these intrinsically explainable methods, like which means probably we cannot trust them too, right? So this post hoc versus intrinsic, right? Like so is kind of like light is whether light is a wave or a particle, right? And so we know that there's a duality here, right? And what we really show in this work is that there's also a duality between post hoc methods and intrinsically interpretable methods. Okay, so our goal is to develop a method, okay, which is post hoc in the sense I train the model, then I can do these analysis, okay. But at the same time, it is also intrinsic in the sense it's going to give me more like, but it's not intrinsic in that way. Like, so, but it is intrinsic in the sense like the pre-training considers this explanation part. Okay, so I'm going to pre-train a model, but this pre-training procedure is going to consider the fact that I'm going to use this model like in tasks where I expect interpretability. Okay, so that is how we merge the intrinsic idea and the post hoc idea, and we expect these models to give explanations, which where they can also say, okay, this explanation is more faithful, or this explanation is not trustable. Okay, so this capability is really, really important if you want to have confidence in the explanations that you're getting, right? So how do we do that? So it so happened that coming up with this problem was much, much harder than coming up with a solution for this problem, okay? So the procedure I'm going to explain to you today, like, it's really simple. You can do this with any masked language model that you're pre-training. It's just adding a little bit of extra computation, but it is going to give you more faithful model, okay? So this is what we are going to do. Like, we are going to take any pre-trained model, okay? So this is more aligned towards masked language modeling. So you can extend this for partial language modeling with a separate project, right? Like, so this is for making masked language models more like faithful, okay? So you take any masked language model which has been already pre-trained. Now you want to perform a task. Typically you go for fine-tuning, right? So what we propose is before you go for fine-tuning, okay, like you do some sort of masked fine-tuning. Okay, so what is masked fine-tuning? So for each training observation, okay, sometimes I'm going to mask things between 0 to 100, and sometimes like I don't mask. So you either see the full sentence with 50% probability, let's say, right? Like, so no masking. And sometimes you're going to mask uniformly between 0 to 100%. Okay. Now the idea here is when you do like this kind of masked fine-tuning, like the model actually sees the mask token with respect to the task itself, right? Like, so in some sense, like whenever there are masks and it cannot make predictions, like the model is learning to do these things like during fine-tuning. So after fine-tuning, when I put mask, okay, first I'm going to verify that these masks are within distribution. Then I will show you that the explanations are more faithful. Okay. So before we reach there, like I want to show you the 0% masked performance for 3 methods. So no masking is the normal MLM. Okay. So no changes. Masking is where I always train it with just masks. Okay. 50-50 is where I train it 50% time with masking, 50% with no masking. Okay. As you can see here, so this is 0% mask performance, which means this is the task performance. Ideally, I want this to be as high as possible, right? Now, no masking is obviously the upper bound here, because when you don't do any mask, the task performance is going to be high. So red is always high, right? But when you mask, your task performance drops. So when you introduce these masks, because you want them to be in distribution, the performance drops, okay? But when you do 50-50 training, like you get performance that is very close to the no masking. Okay, so now let's look at the 100% mask performance. So what do I mean by 100% mask performance? Like I mask everything. When I mask everything, I want the performance to be close to random, right? Like model cannot make a prediction, right? And as you can see here, when you mask everything, like both masking and 50-50 masking, right? Like so they are like they are kind of equal. Like so they like you get the benefits of masking. Like when you need masking, you get the benefits of not masking, like when you don't need the masking. Okay. So once you have this setup, then you should verify that when the masks are within the distribution. Okay, so I'm not going to explain how we do that here. Like so, but here you see a bunch of importance measured in the literature. For all these importance measured, like once you do the mask fine tuning, like we do some statistical tests to verify that the mask is within the distribution. Okay. So only when the mask is within the distribution, then you can go verify the faithfulness. Okay. Now, here you see the different importance measure from the literature. Okay. And the pink is the random one. Okay. So a faithful importance measure will have performance less than the random. Okay. So because what does this mean is like, so basically for different masking ratio, right? So what is the effect, right? So this is random masking. So if your masking is meaningful, it should have significant degradation than a random masking, okay? And as you can see here, because of this masked fine-tuning training, like we were able to make some of the occlusion-based methods much more faithful than what they were previously before. Okay, so this is really a simple technique to make MLMs more interpretable. Like, so all you have to do is to do masked fine-tuning instead of normal fine-tuning. Then you just do a verification that everything is in distribution, right? Like, and then you can measure interpretability and the faithfulness of interpretability. Okay. Okay. So I'll take a few minutes for the. I'll take 5 minutes to finish. Okay. So I want to ask one last question, which is like once you interpret these models, like you can discover biases, right? And so there's going to be a lot of biases. And how do I reduce these biases? Like, so how can I make these models more fair? So we have several projects along this direction, but I'm just going to highlight one of them. Okay, so which is currently under, this is also under DML. Okay, so but the work is in archive if you want to read. So this is the work done by my PhD student Abdul and my postdoc Gonzalo. So here we propose a really simple technique to take any pre-trained large language model and make it more fair just by tuning the attention. Okay, so before I show you the idea, so this is like an outline of various methods for debiasing LLMs. Okay, so there are pre-processing methods where like you take the data set and you pre-process the data set such that the model can be more fair. There are in-processing methods which changes things during the model training. There are intra-processing methods like which basically takes the trained model and modify the weights. And there are post-processing methods which takes the predictions of the model and make some changes to make them more fair, right? And so what I'm going to propose today is an intra-processing method, okay? So which takes a pre-trained model weight. It does some modifications to the architecture to make them more fair, okay? So we are going to work with attention, okay? So here you see like a result from this ACER 2022 paper where they showed that if you dilute the attention, like, or if you if you maximize the entropy of attention, let's say, then you're going to get more fair models. Why? Because if you have a sentence like this, she looks depressed, okay, and if the model puts so much weight on she, then that is a bias, right? Like, so when you maximize the entropy of this attention, like you spread this weight across these words, then you have a less biased model, right? So this was the premise for this Atanasio et al. ISO 2022, okay? So this was the kind of motivating paper for our project. Like, so we started thinking, is it always true that maximizing the entropy of attention leads to more fair models, right? Like if so, we should all be doing that in every task, right? So I can give you counter examples where this is a bad idea. Okay, so this is an example where the sentences he seems delighted, and the model was really not putting any weight on he. Okay, but when you diffuse his attention, when you maximize the entropy, you are asking the model to look at he too, right? So in some sense, playing with this entropy, like so, could also hurt the fairness, right? So what should we do? Like maybe we should not play with the attention, but it's an easy thing to do, right? Like so, like you have a pre-trained model, if you can just play with the attention somehow in a careful way, such that like you can reduce the fairness, that would be nice. So what we propose is like do the same thing, but in a more data-driven fashion. Okay, so like previously people were trying to maximize the entropy, like the opposite is like minimizing the entropy, right? Like so minimizing the entropy is also not a good idea because sometimes maybe you put all the entropy to he or she in the sentences, right? Like so what we propose is to somehow find the right level of entropy, like that would minimize the bias, okay, for these attention mechanisms. So here you see like different, in the x-axis you see a beta parameter, which is basically scaling the entropy of these attention mechanisms. And as you see, you do anything with the entropy of this attention, your performance is going to degrade, right? But there's actually some sweet spot in terms of the fairness. Let's say you could have, if you trade off a little bit of performance, you could get more fair models. And you can get all these things by just tuning the attention, like instead of training the model. Yeah.
Just out of curiosity, how do you measure fairness?
Okay, that's a good question. So I think in this case, it's demographic parity. There are many metrics for measuring fairness, and it also depends on the task and the data set. Okay, I think in this case, it's demographic parity. Okay, so what we really need is entropy modulation, not maximization, right? Like so, like here, I'm going to quickly go through the results. Like EAT is our method, which is doing the entropy modulation. Okay. So what I want to show is basically it's better than other methods, and like we can also combine this method like with other methods because it is complementary, right? And you get even better performance. So I'll just show you some qualitative examples. Like so here, given a prompt, the United Nations of Islam is an African American, right? Like so the vanilla one is like biased. When you do random perturbations, things are biased. But EAT is not that biased, okay? So there is not a lot of work in debiasing generative models. Like there's a lot of work in debiasing classification models, but for generative models, like there's not a lot of work, okay? So, here's another qualitative result where like vanilla models were mostly focusing on the fact that she's a woman, and EAT is a bit less biased again, okay? But this paper is available online, so you can go read it in detail. Okay, so to summarize, like I talked about a bunch of issues and potentially how we can reduce these limitations or incorporate this idea that these are limited when you consider downstream applications, right? But there is a lot more to be done. Like so, like for example, how to design factually grounded LLMs is an open research question. Like so, our first project gave some hint on what is going wrong, right? Like so maybe if you have better knowledge models, then we won't have this hallucinations anymore, right? Like so, and the other important thing I would like to highlight is most of these LLMs are pretty naive in the sense they don't have any memory, right? Like, there's parametric memory of code, like but if you really care about general purpose algorithms like a true AI system, right? Like so, like memory is one of the core capabilities of any intelligent systems, and these models don't have that persistent memory. And we do a lot of projects on how to efficiently pre-train these. Like I did not even talk about them here. Like it's an important practical research question because if you can speed up the training even by 2x, you save money like from $20 million to $10 million, right? So how to accelerate the training of these models, how to be more sample efficient is an extremely important question. And how to design LLMs that can continually update their knowledge, right? That is also another important question, which we don't have a good answer for. This is important if you don't want to pre-train again and again. Like, so imagine you continually train a model in a lifelong learning fashion. Like, so there's only one model which you train every year by updating its knowledge, right? But that's much more manageable than training the model from scratch every time. Like, for example, Facebook trained Llama models, like first version, then they trained from scratch Llama V2, right? Like, and OpenAI is doing GPT-1, GPT-2, GPT-3, and they're all pre-trained from scratch, right? Like, so how to continue to train these models? Like, that's another question that is really important. And handling multiple modalities, I think that is happening already. You can see that OpenAI's ChatGPT has like multiple modalities now. Like, so, but you have more challenges when there are multiple modalities, right? And lastly, like I showed you this trend in the beginning that the models has to get bigger and bigger for superior performance. But I don't believe in the emergent capabilities that comes with larger models. Okay, so I'm pretty sure that in 5 to 10 years, you will have models at the scale of BERT, but has all the benefits that you could get from GPT. Okay, so how to reach there? That requires more rigorous scientific research on trying to understand what is really happening in these LLM training, right? Like, so currently everything looks like a mystery, but I'm sure we can reason things, and those reasons will help us design more efficient LLMs. Okay, so one thing that I want to finish this talk with is like, I want to highlight that LLMs are general purpose pre-trained models, okay, but they are not AGI, okay, as a lot of people claim. Like, so we saw a lot of fundamental limitations today, but there are many other limitations. Like, so not having memory, not having good reasoning capabilities. Like, so, like I could put another bunch of reasons why they are not AGI. Okay, so like I think this temptation to connect LLMs with AGI is really like for marketing purposes. So we don't have a general purpose algorithm like that is a true AGI. Okay, so these are, I consider these as like really useful initialization methods. Now, these are better initializations than random initialization. So if you think about it this way, it opens up for a lot of interesting academic research too. Like, you don't need to pre-train LLMs. Like, so you can take these pre-trained LLMs as initializations. Now think about what kind of tasks that you could solve with this better initialization instead of random initialization, right? So these are, okay, why did I have a animation here? So these are the list of papers that I covered today. I decided to talk mostly about unpublished work because most of the published work are out there already. And I think 4 out of 5 are under review at EMLP. Okay, so I'm hoping that all of them will get accepted this Friday. Let's see. Thank you.